there's some positive n, where you take the nth power of it, it becomes the zero matrix. Zero here is not a number, but it's a matrix, n by n matrix, so k by k matrix. It's a square matrix where all the entries are zero. If this happens for some n, then it's called nilpotent. Right? Now, nilpotent will later be used when we do the Jordan normal form. But for now, let me give you this idea that so this will be something that you will learn later. So here's a theorem. If A is nilpotent, then for some P, P inverse would be strictly upper triangular, meaning that is 0 here, 0 here, diagonal entries are 0, 0 in the lower, and then you only get non-zero elements if there are any. Some of these could be 0, or most of these could be 0, but if there are any non-zero element, it has to be above the diagonal. That's called strictly upper triangular. Okay? So this is called strictly upper triangular. Now, if you drop the word strictly, that means you can have non-zero elements on the diagonals as well. So that would be just upper triangular. Strictly upper triangular means that diagonal has to be zeros, and then only non-zero ones will be above the diagonal. Okay. Now, if you look at some of these examples and try out what happens to these matrices, then you can kind of see why such a matrix would be nilpotent. So if you had a 3 by 3 matrix with 3 non-zero entries, and if you did a square of this, you'll see that at the first iteration, the next diagonal line above the diagonal will be zeros, and you get this. And then, therefore, if you take the third power, the same thing, third power, you get 0, 0, 0, 0, 0, 0. Okay? And then, same thing happens for 4 by 4. If you have 4 by 4 and you have 0, 0, 0, 0, and then you have some non-zero entries here, then taking a square will immediately delete the one above the diagonal, and now you will have this. Okay? It'll be 0 down here. And then if you take the third power of this, you're going to have 0 and then 0. If you take the fourth power, it will be completely 0. Okay? So what that tells us is that you'll see that later when we learn the Jordan normal form, we're going to revisit this. You'll see that if a 2 by 2 matrix is nilpotent, then its square has to be 0. It already has to be 0 by square. If a 3 by 3 matrix is nilpotent, then A square is the last time you can have a non-zero matrix. A cubed, it has to be 0. Okay? It could be 0 beforehand, but A square will be the last time you have a non-zero thing. If you have a 4 by 4, the last time you can have a non-zero thing is when you have A cubed. Then after that, A to the 4th, it has to be 0. So that's what you're going to learn later. With Jordan normal form, all of this will make sense. Okay. Now, another thing is, you could very well have lower triangular too. So you can write down the same theorem. You can have another different type of P that could make it be strictly lower triangular. So that will be another case when you have a nilpotent ones. And those, if this was down here instead, if you flip it, if you take the transpose, you can say the exact same thing. Okay? All right, so with that knowledge, this question is kind of straightforward. See, if you want the simplest example of two nilpotent matrices whose sum is not nilpotent, and you think about 2 by 2, what's an easy example of a 2 by 2 matrix that's like this one? What's a strictly upper triangular 2 by 2 matrix?
0, 1, and
0, 1, 0, 0, right? That will be a strictly upper triangular one. You could very well put a 2 or 4, whatever number here, but 1's the simplest, right? So this is as simple as 1. And of course, if you square this, you get 0, 0, 0, 0. Because the next level will be 0. Same thing can be said of 0, 0, 1, 0. So these are both nilpotent matrices. But what if you add the 2? You get 0, 1, 1, 0, right? So take this matrix and let's try to square this. Well, let's do the computation. Across, down, right? 0 times 0, 1 times 1, what's that? 1, right? 0 times 0, 0 times 1 plus 1 times 0, what's that? 0. 1 times 0 is 0, 0 times 1 is
0.
No, sorry. 1 times 1 is 1, 0 times 0 is 0, so it's 1. Oh, okay, so this squares to the identity matrix, right? So any even-powered one would be squared to the nth power, but squares to the identity matrix, so it's the identity matrix to the nth power. What's that? Identity matrix, no matter how many times you take the power of, you get just the identity, right? So all the even powers will be identity. You have a question?
Yeah, could you do that matrix again?
0 times 0, 1 times 1 is 1, right?
Oh, okay.
0 times 1, 1 times 0, those are both zeros, it's 0. 1 times 0, 0 times 1, they're both 0, so it adds up to 1, 0. 1 times 1 is 1, 0 times 0 is 0, so if you add, it's 1. Okay. All right, and then if you have any odd ones, what do we know? That's 0, 1, 1, 0 to the even power times another 0, 1, 1, 0. But since we know that this is an identity, we recover the original one, right? So, is this nilpotent? Never. It never becomes 0. No power of this matrix would give you 0. Therefore, it's an example where sum of two nilpotent matrices is not necessarily nilpotent. Okay?